we're going to look at some more calculus here in terms of the economics of the calculus. We're going to look at functions of many variables, and two common functions in economics are the utility function, which I'll write as utility is a function of phi, q1, q2 to qn. And the other one is a production function. Y is a function of x1, x2 to xm, where the q is referred to final goods and the x is to input. We're going to look at the production function in a bit more detail. And we've constructed three isoquants here for labor on the horizontal axes and capital on the vertical axes. Unlike difference in difference curves, one cannot do monotonic transformations of production functions, and we'll see that a little bit later on in this lecture. Isoquants and indifference curves are called level curves, which are a projection from 3 dimensions in the positive plane to 2 dimensions. So let's assume the following production function. Let's assume that we have what's called a Cobb-Douglas production function, where output y is a function of some fixed parameter a times L, which is labor, raised to the power alpha, and k, capital, raised to the power beta, where both alpha and beta lie between 0 and 1. We can take the first derivatives of y with respect to labor and capital, and that gives us, respectively, the marginal product of labor and the marginal product of capital. Doing so, we find that the marginal product of labor is A times alpha, L, alpha minus 1, K over beta. And you can see that if we take the K beta, alpha, and the A out, we basically get Y, and we're left here with an L minus 1 and an alpha. So we put the alpha here and the L underneath. So the marginal product is given by alpha Y over L. And we could do the similar thing for capital, where the first derivative of that production function is capital A times beta, L to the alpha, K to the beta minus 1, and we can write that as beta Y over K. Now we can also take the second derivatives of the production function with respect to labor and capital, and we denote that by F subscript LL, which is the partial derivative of marginal product of labor with respect to labor. And we conduct that through, and we get A alpha, alpha minus 1, L alpha minus 2, and K to the beta. And we can write that again using the same thing we did to get this alpha Y over L. We get alpha times alpha minus 1 Y over L squared. Doing the same thing for capital, we get the derivative of the partial derivative of the marginal product for capital with respect to capital, and we get beta times beta minus 1 Y over K squared with this intermediate step here. And of course, we can get the cross product, if you like, which is the partial derivative, the second partial derivative of the production function with respect to labor and capital, and we denote that FLK, and it turns out that this is equal to FKL. So it doesn't matter if you first find the marginal product of labor or the marginal product of capital, and then take the partial derivative of that with respect to the other input. And when we do that, we get alpha beta over LK times Y. And again, we have this intermediate step. So this particular expression gives you the effect on the marginal product of capital or on the marginal product of labor from changes in the amount of labor or capital that's employed. And this could be very important because we could have that the more labor you have, the more efficient capital becomes, or vice versa, or even worse. Now, there's also the concept of a total derivative, and I think we've encountered that previously, but just in case, let's just write a general production function as y, a function of 4 inputs, x1 through x4. We take the total derivative by taking dy, the first derivative, so the partial of the function f with respect to x1, multiplied by dx1 plus f2 dx2. And remember, these f1, f2, f3, f4 are marginal products. and these are the small changes in x1, x2, x3, and x4. So more generally, we can write this as the total derivative of output y is equal to the sum of all the partial derivatives times their the little changes in those particular inputs. So this represents movements along a hyperplane tangent to an n-dimensional surface suspended in n space. And when I read that, I think more of string theory than I do of economics, I must admit. Mathematical difference between the utility and the production function. All right, that's important because they are very, very close. The way we solve problems in production and the way we solve problems in consumption or consumer demand theory, they're very similar. So both are examples of scale types. That's the important thing. But permissible transformations of scales differ between the consumer and producer problems, as indicated in this table. So here we have admissible transformations. All right. One is an identity where the phi of x is equal to x, and the scale type is absolute. And a good example of that is just counting 1, 2, 3, 4, etc. Another is a similarity transformation, where we take the original and we multiply it by a constant alpha, which is greater than 0, and this is a ratio. And to give you an example of that, consider mass, kilograms to pounds, or time intervals, or temperature, degrees Kelvin. That's a ratio. And I'm not sure if I got that mass correctly. I don't. Where mass can be measured in two different ways, kilograms or pounds. And I think that ratio holds. So I think similarity works in this case, but it doesn't in the case of temperature, as we'll see in a second. Then there's third kind of scale or kind of admissible transformation is a positive linear transformation. So we go alpha x, much like the similarity transformation, but now we're adding this beta. And of course, alpha again is greater than 0. Beta could be positive or negative. And that's an interval. And to give you an example, temperature, degrees Celsius and degrees Fahrenheit. And they differ by alpha, and we'll tell you what this alpha is in a minute, and they differ by this beta. Calendar time, the same kind of idea. The fourth kind of transformation is a monotonic increasing transformation, where x is greater than or equal to y as long as phi of x is greater than or equal to phi of y. All right, we call this an ordinal scale type. So think of utility functions are ordinal, or in other words, preferences are an ordinal idea. Hardness, there are measures of how hard a surface is. Air quality is some kind of an index or scale. Grades of grain or grades of lumber are another example here. And then we have any one-to-one transformation phi, and this is a nominal one. Think of numbers on the back of a uniform. All right. So if Messi, for example, is wearing number 2, it doesn't matter if it's number 2 or number 22. It's still Messi. He's a soccer player, in case you don't know. Labels on alternative plans. All right, we might have a plan labeled A, B, C, but it could be CBA as well. It's just a way to identify the plan, or in the case of uniform numbers, to identify the player. So some further examples. Grain output can be measured in bushels per acre or tons per hectare. Since 0 is the same, if you have 0 crop, then basically it'll be 0 for bushels an acre and it'll be 0 for tons a hectare. So only a similarity transformation in this case is permitted, where phi x is equal to alpha x. So there's a simple way to transform bushels per acre into tons per hectare by identifying what that alpha would be. In terms of mass, for example, you would have pounds to kilograms. You'd multiply the pounds by 2, divide by 2.2 to get kilograms. And then there's the Fahrenheit to centigrade, which is a positive linear transformation with alpha being 5/9, and beta 160/9. A linear transformation preserves the distance between iso curves. With a cardinal utility, only a linear transformation is permitted, but with ordinal utility, a monotonic increasing transformation is permitted. And in this case, what we have is U Q1, Q2 is equal to FU. So we're taking the utility function U and we're transforming it with this monotonic function F. So we write F as a function of phi, which is a function in turn of Q1 and Q2, as long as F prime, the first derivative of F with respect to the utility function, is positive, the ranking is preserved. Now, let's let U be equal to phi Q1, Q2. So in other words, we're just going to have where the utility function is Q1 times Q2. And the transformation V is the log of this original function U, and that gives us the log of Q1 times Q2. And I think that's, I won't go there. The partial of the new utility function, V, with respect to Q1 is equal to dV with respect to U, and then the derivative of U with respect to Q1. So we get 1 over U. All right, remember that's a log. It's the log, and the derivative of a log is 1 over U in this case. And then the derivative, the partial of the utility function with respect to Q1, which gives us 1 over Q1, Q2 times Q2 gives us 1 over Q1. Similarly, the transformed utility function V with respect to, if we take the partial with respect to Q2, we get 1 over Q2. What's changed? Well, the ranking has not changed by definition, as we saw in the table above. The original marginal utility of 1 was Q2. So if we go to this function here and we take the marginal utility with respect to Q1, we simply get Q2. If we take the derivative of this with respect to Q2, we get Q1. So U1 over U2 is equal to Q2 over Q1. And that, remember, is our condition for, that's our condition for an equilibrium. All right, this function here, or that relationship there. Now, if we look at the transformed function, then marginal utility of 1 is 1 over Q1, marginal utility of 2 is 1 over Q2, and again, U1 over U2 is equal to 1 over Q1 divided by 1 over Q2, and we get exactly the same result as we had before, which is Q2 over Q1. So in that regard, these two are identical, and we've shown that the transformed utility function gives the same results as the original utility function. So that in the end, there is no difference in the demand functions when you do that. All right, now suppose we have a production function that's given by this, and we find the total derivative as usual over the n inputs, and we find that along any level curve, we set that equal to 0. So we've done that here. So for n equals 2, so we have a polynomial of 2. So in other words, we just have this component. Then we get f1 dx1 plus f2 dx2 equals 0. which when we solve this is dx2 over dx1 is minus f1 over f2, assuming of course that f2 is not equal to 0. Then in the case of utility, we get dq2 over dq1 is minus phi1 over phi2, which is basically phi1 is your marginal utility of 1, marginal utility of 2. Now returning back to the production one, we get dk over dl, which is minus f of L following this. So in other words, this becomes K, this becomes L, this then is L, and that one is K. So we have minus FL over f of x, f subscript x, which is equal to the negative of the marginal product of labor divided by the marginal product of capital. And we can draw that particular isoquant, because that's what this is an isoquant. And we see that is just looks like this. It's downward sloping, convex to the origin. Since F1 is positive, F2 is positive, the isoquant has to have a negative slope. All right, F1 is positive, or FL is positive, and FK is positive, so we have a negative slope of that isoquant. If the second derivative of x2 with respect to x1 squared, then we have an increasing marginal rate of technical substitution. So in other words, we take this derivative and we take the first derivative of it with respect to one of the inputs, and we get increasing marginal rate of technical substitution. All right, and what that means is that these level curves are convex to the origin. So let's look at that second derivative. So the first derivative, as we saw in the case of two goods, is simply minus the marginal product of the first one divided by the marginal product of the second input. Now take the second derivative with respect to x1, the second derivative. So we're going to basically take the derivative with respect to x1. It becomes a little bit more complicated. So we put this minus 1 over f2 squared, because this is the formula that we use for when we have what do we call that again? A ratio, if you like, one divided by the other. And when we take the first derivative, it's equal to f2 times, so the bottom times the derivative of the top minus the top times the derivative of the bottom. We now simplify that, or we expand it rather first, and we get this result here minus this result here, because we have to take into account the fact that when we take the derivative of f1 with respect to x1, we get first off the derivative f11, and then we get the derivative of x2 with respect to x1, and then so we have f1 1 times the derivative of x2 times x1. All right, so here's where the explanation is a bit better. We have f2, derivative of f1 with respect to x1, dx1 over dx1. That is simply 1. So this is 1.0. And then we have the partial of the marginal utility of 1 with respect to x2, derivative of x2 with respect to x1, and that should be a, let me just get this straight, that's a derivative, not a partial derivative here. And we do the same thing for the second term, for this term here, and it gets quite complicated. We simplify that and it looks like this. And recalling that dx2 over dx1 is simply the ratio of negative of f1 over f2. We plug that in here, and we solve through, and in the end we get 1 over f2 cubed times this in brackets. Now, if this expression is to be greater than 0, which is the case if it's a minimum, then this occurs only if this f2 squared f11 minus 2 f1 f2 f12 plus f1 squared f22. Notice that we've multiplied that negative out. All right, it has to be less than 0 since f2 is greater than 0. So that implies if we have diminishing marginal utility or diminishing marginal product, then f11, the derivative of the marginal product with respect to the first input, when we take the derivative of that with respect to the first input again, then we get that less than 0, and f22, the same thing. So if you think of this as a utility function, then we have the derivative of the marginal utility of 1 with respect to good 2, and that's less than 0 because we have diminishing marginal utility. And the same thing for the second good. So we can sign this as negative, all right, because f2 squared is positive, f1 squared is positive, f22 is less than 0, so this one is negative as well. But we don't know what this term f12 is, whether it's greater than or less than 0. If it's negative and large, then this is less than 0. Otherwise, it's greater than 0, and in that case, this whole thing will be negative if this is a positive number. But if this is a negative number and if it's large enough, then it'll be that this will be less than 0, all right, which is not what we want if we're maximizing. Comparative statics, the mathematical technique to investigate if refutable hypotheses are forthcoming. If not, if you can't get a refutable hypothesis, then actual empirical testing is a waste of time, since no data can ever refute the theory. So you're dealing with a theory, and I brought up string theory. The problem with string theory, from what I gather, is that there are really not very many empirical hypotheses that you can test. Suppose that we have 3 alternative hypotheses. Firms maximize profit, so they maximize total revenue minus total cost, or they maximize the utility of profit, where the first derivative of utility of profit is positive. That means that if you have more profit, your utility goes up. And the third possibility is that firms maximize their sales or their total revenue. So what is the profit equal to? Well, it's equal to total revenue. So it's price times quantity minus the C of X, the cost of production, and it's a function of the amount of output. So here we're talking about output, not inputs, minus the tax on output. So with no taxes, if t equals 0, then we simply get that r prime x equals c prime x, which of course is a value judgment because it's a value judgment that firms produce where marginal revenue equals marginal cost. With taxes, we get the same result, but now we notice that that x is a function of the tax. So our output will be a function of the tax, and we have to include that tax here if we take a first derivative. So at our optimum, and we denote the optimum just as a reminder as x star, so if we have a star on it, it's our optimum value. We differentiate with respect to the tax, so we differentiate this equation with respect to the tax. We get the second derivative of the total revenue times dx over dt minus the second derivative of the total cost times dx over dt minus 1. That comes from here, equal to 0, assuming that this is not equal to 0, all right? And of course, that only occurs if we're not in perfect competition, because in perfect competition, remember, we set the marginal cost equal to the price, where the price is the marginal revenue in this case. But in monopoly, there's a divergence between price. Price will be higher than marginal revenue. So assuming that this is not equal to 0, we get dx star dt equals 1 over the second derivative of r minus the second derivative of the cost function. All right. And if it was 0, we couldn't divide through. So this case, the second derivative of the total revenue minus second derivative of total cost is less than 0 by second order conditions. This results from the comparative statics, and we can test if output falls if taxes increase. So this tells us that output falls as the tax increase. So you raise this, and this will go down. All right, this will be positive, that'll be negative, so that's 0. If the tax goes down, then this is negative, so this has to be positive, so that means that this is less than 0. All right, the second option here was that the utility function was, that utility was a function of profit, and we have u, and then we write the profit here as Rx minus Cx minus Tx. The first order condition is that the derivative of u with respect to pi times the derivative of pi with respect to x is equal to u prime pi, and then we get this same expression here, which is equal to 0. Since this number here is greater than 0, we can get rid of it because it cancels with the 0, so we divide through by this number, divide through over here, and we still get 0. And what happens is we get the same result as in 1, the same comparative statics as in 1. That is, output falls if taxes increase. So there's nothing new here, so there's no real thing that we can do to come up with something better than the profit maximizing situation. Now we can also consider maximizing sales, and in that case we have revenue x minus t of x, so the revenue from sales is what we're really maximizing. And the first order condition is that the first derivative of the sales is equal to the first derivative of the total cost minus tax. So the first derivative of the total revenue, I meant to say total revenue minus tax, this is just the marginal revenue is equal to the tax. X is an implicit function of the tax, t, so then we get this result here is that the first derivative of sales is equal to the marginal revenue minus tax equals 0. We look at the second order condition, where the second derivative of the revenue function, or the first derivative of revenue with respect to x times dx over dt is equal to 1. And that implies that dx dt is equal to 1 over the derivative of the marginal revenue with respect to x has to be less than 0. And unless revenue and cost functions are known, no observations or changes in taxes, nor any changes in sales can distinguish between the theories. So finally, assume the firm is a price taker, so that we get pi profit equals px minus cx. The first order condition gives us price minus marginal cost, which means marginal revenue is equal to price equals marginal cost. Second order condition is simply that the first derivative of the marginal cost with respect to the x is less than 0. That tells us that the marginal cost slopes up, so this has to be greater than 0. Solving for x as a function of p gives supply. So we solve that function here. For p, we get the supply, p minus marginal cost is equal to 0. We differentiate with respect to the price, and we get 1 minus the first derivative of marginal cost with respect to quantity times the derivative of quantity with respect to price is equal to 0. Rearranging that, we end up with dx dp is equivalent to 1 over that second order condition greater than 0, since the second derivative of the cost function has to be positive by the second order condition. If price facing competitive firm is raised in some way, output increases. So if the price facing a competitive firm is raised, then output increases. In other words, supply is upward sloping. And again, we have some kind of a testable hypothesis. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.